Hello teacher, my name is T and I'm from Group Friday. My group's members are Miss Phương and Mr. Sang. Our group will present about recommender systems. The mini project, the objective of it is to research the three models. The first one is content-based recommendation. The second one is collaborative featuring recommender system. And the final one is I-Autorec model. That is from the paper G Local K for recommender systems. And now the three models will solve a problem where the input is user, item, available ratings, and the output is the missing rating. So now I will talk about some general features of each model. For the first one, content-based. This model evaluates the properties of each item by using feature vector and then use this feature vector to predict rating, missing rating. And the second model, collaborative featuring, will rely on the similarity between two users or two items and then predict missing rating. And the final one, I-Autorec, item autorec, is a combination between autoencoder and collaborative filtering systems. As you might know, the autoencoder will generalize sparsely observed metric entries to a low-dimensional feature space, and Autorec designed an item-based autoencoder which takes high-dimensional metric entries, projects them into a low-dimensional latent hidden space, and then reconstructs the entries in the output space to predict missing ratings. For Autorec, the model also used the two kernels to do this task. Okay, now we will go into details about background related to each model. I will talk about background related to content-based recommendation. So over here we see a matrix called utility matrix. The rows of this matrix are items and the columns are users, and the numbers over here represents for the rating, and the question marks represent for missing rating, and our group will predict these missing ratings. Okay, so now how to build a utility matrix. So we can ask the user to rate the product like the way Amazon do. They send emails to their customer to remind them to rate for their products. And the second way is based on users' behavior. So you see our utility matrix now include one more column called items feature vector. So we will build an items feature vector for each item, and over here we build a vector with two components. The first one represents for the level of Bolero, and the second one represents for the level of children. So if the first one is high, that means the item belongs to the Bolero song. And if the second one is high, the item belongs to the children's song. Okay, and this feature vector represents for item profiles. Now we will consider our model. So our group choose linear model to for each user. So each user will have one model. So now let's take a look at the equation 1. The xm over here is the item feature of item m, and bn over here is the bias of the user n, and ymn is the rating of user n for item m, and we need to find the weight n by minimize the loss function. So this one is the formula for the loss function, and our group use regularization L2 to avoid overfitting situation.
Another way to is using for the recommender system is collaborative filtering. Recommend the idea is that looking at the user that are the most similar to you in this sense and recommending items that this user like, and the process of identifying similar user and recommending what similar user like is called collaborative filtering. For example, we have the utility matrix introduced here that user A, B, C, D and the rating for the items movies in this utility matrix, and we need to deal with how to measure similarity of user or item from their rows or columns in the utility matrix. Here are some ways to measure similarity. The first is check at similarity. For example, A and B have an intersection of side 1 and a union of side 5, so their check-out similarity is 1/5 and their check-out distance is 4/5. The second is using the cosine distance. With this formula, so the cosine of the angle between A and B. A is 0.38. The third is routing the data. We could try to eliminate the apparent similarity between movies a user rates highly and those with low score by routing their ratings. For example, we could consider rating of 5, 4, and 5, 3, 4, and 5 as 1, and consider rating 1 and 2 as unrated. And final is normalizing ratings. If we normalize rating by subtracting from each rating the average rating of that user, we turn low ratings into negative numbers and high rating into positive numbers. If then we take the cosine distance, we could find that with opposite view of the movies they view in common, we have the vectors in almost opposite directions and consider as far as possible. So the cosine of the angle between A and B is 0.092. In the final, the predicted rating frequently determined by weighted means of K rating for item I. This is a popular formula to determine this.
So to continue the presentation, we would like to introduce another approach that called the global local kernel-based matrix framework. It can be called GLOCAL. This method aims to generate and represent a high-dimensional sparse user item matrix into a low-dimensional space with a small number of important features. Our GLOCAL can be divided into two main stages. The first one is the pre-training, which shown on the left hand side, and the second one is the fine-tuning, shown on the right hand side. For the pre-training step, we pre-train an autoencoder with the local kernelized weight matrix, which transforms the data from one space into the feature base using the 2D radial basic function kernel. Then the pre-trained autoencoder is fine-tuned with the rating matrix produced by a convolution-based global kernel which captures the characteristic of each item. So come to the detail for the autoencoder pre-training step. We first deploy and train an item-based autoencoder which takes each item vector Ri as input and the output is the reconstructed vector Ri quote to predict the missing rating, and the model is represented at the equation 1 where the We and Wd is the weight matrix, B and B quote are the bias vector, F and G are nonlinear activation function. Next, the weight matrix We and Wd in equation 1 are reparameterized by a 2D RBF kernel named local kernelized weight matrix, and the RBF kernel can be defined at equation 2 where K is the RBF kernel function which compute the similarity between two sets of vector U and vector V. Then we can compute the local kernelized weight matrix at equation 3 where W quote is computed by the Hadamard product of the weights and the kernel matrix to get the specified weight matrix. After finish the step of retraining, we come to the fine tuning step. But we will compute the global kernel-based rating matrix. We fine-tune the pre-trained autoencoder with the rating matrix produced by the global convolutional kernel. The whole construction procedure can be defined in the following equation 4, 5, and 6. After we have the reconstructed rating matrix in the retraining step, we will apply item-based average pooling to summarize the information of each item in the rating matrix, which show in equation 4 and in equation 5. These kernels are aggregated by using an inner product. Then we apply a global kernel-based convolution operation to the user item rating matrix for the global kernel-based feature extraction. In equation 6, R hash is the global kernel-based rating matrix which is used as an input for the fine-tuning. After that, we will do the step of autoencoder fine-tuning, the reconstruct result from the fine-tuned autoencoder correspond to the final predict rating for the matrix completion in the recombinant system.
The second part of our representation is about implementation of each model. I will talk about how to implement the content-based recommendation model. So first, I will read the rating files by using the pandas library, and then I split that file into the two datasets. The first one training and the second one is testing. So over here you can see the rate train and the rate test. Okay, so after I read the rating file, I will see the data frame like this, and I split this data set into two parts. The first one training set and the second one test set. They are 90,570 rays in training set and 9,430 rays in test set. In the similar way, I also read the user file, and over here is what I see. So they are 943 users. And now After I read the item files, I will see a data frame like this. So besides some common feature of each item, we have some special attributes over here. So they are categories of the given items. So if you see the number 1, that means the item belong to the given categories. On the other hand, if you see the number 0, that means the item does not belong to the given category. And one item can belong to more than one category, and will rely on this data to build items feature factory. How do we do that? We will use the TF-IDF score to build the feature factory of each item. So TF-IDF stands for term frequency inverse document frequency of records. It can be defined as the calculation of how a relevant word in a series or a corpus is to a text. So if you get the high TF-IDF score for a word, that means that word is more relevant to the given text than the other words. Okay, so from the library scikit-learn, I import TF-IDF transformer, and then I use auto-norm in order that the value of TF-IDF score can belong to a range from 0 to 1, and I will use TF-IDF score as the feature vector of each item. So each row over here will be one feature vector for one item. And now I build a function where the input is rate matrix user index, and the output is item index and the score. The score means the rating for the item. Okay, and then I use the model read over here, read regression, as I mentioned before. So to find the weight matrix W. So after I get the weight matrix W, I times it by the TF-IDF score. In other words, I times it by the X, and then I plus the bias to get the predicted score, the predicted rating. Yeah. And over here I show some predicted rating and the two rating and the corresponding index over here.
This is the implementations of the collaborative filtering. We create the utility matrix, user, or even we could use the item or item. And next, we normalize utility matrix and similarity matrix. And we're using the predict ratings by find all user who rate I and find similarity between the current user and others who already rated I, and I item find the K most similarity user and the corresponding similarity levels. And finally, we recommending the items for this user.
Next is the implementation of the glocalK method. We did the experiment with two completion datasets of Movieland. Movieland 100,000 denoted as ml 100k, and Movieland 1 million rating denoted as ml 1m. For the ml 100k dataset, it contains 100,000 rating of 1,682 movie max by 943 users, and for the ML1M it contains 1 million rating up around 3,700 movies made by more than 6,000 users. In the ML100K, there are several files for training and testing. The file with extension.base is for training and .test is used for testing. We use two files ua.base and ua.test for training and for testing. For the ML1M, it's a little bit different. It keeps the rating matrix inside a single file so that we have to read and split the dataset into two subsets with the ratio of 90 and 10 for training and for testing. Next is the environmental setup. To approach the way of training data on the cloud, we use Google Colab as an environment for training the model. User can easily create a Python notebook, which is quite similar to the Jupyter notebook in just a few clicks. Colab provides for every user a free Tesla K80 GPU, which can help users accelerate their deep learning application. You do not need any external configuration when using this library. Just import the module and coding on it. So next is the hyperparameter setup. We use two 500 dimensional hidden layer for autoencoder, a 5-dimensional vector UI and VJ for radio basic function kernel. We use only a single convolution layer with a 3 by 3 size global kernel. LBFGSB optimizer has been applied to minimize the regularized square error where L2 regularization is applied with different penalty parameters lambda 2 and lambda s for the weight and the kernel matrix. In the next, we will talk about the pre-training step of the local kernel. Um, Firstly, we will define the RBF kernel in the equation 2 as in the figure below, where we take one item UI and one item VJ of the whole vector U and J to the local kernel to calculate the similarity between them. And secondly, with each item U and V, we can calculate the respective weight value WH from the local kernel, which we have already defined. After that, we will do the step that we call local kernelize the weight matrix by we apply the Hamada dot product of that of the weight matrix to the WH, and after that we will multiply that WEFF with the original rating matrix plus with the BB is the bias vector, and we put them through the activation function, so it will give you the result is the reconstructor matrix of the local kernel retraining step. And for the global kernel, in equation 4, 5, and 6, we will do some steps. First, we will apply the average boolean on the previous reconstruct uh, rating matrix so that we can uh, get the summary of each item, and after we have the summary we can put them together by the dot product to create a global kernel. After that, that global kernel will be applied with the convolutional operator on the origin rating matrix to get a global kernel based matrix, and it will be used as an input for the fine tuning.
The final part of our representation is about evaluation of each model. I will show you the way to evaluate the content-based recommendation model. So, as I mentioned before, when we build the loss function, we use the mean, the square error, but for evaluation, our model I use RMSE, root mean squared error, and here is the code I wrote for root mean squared error. So over here you can see the error between the scores truth and the scores predict, and then we double it, we times it by itself, and then we divide by the total number, and then we take the square root of this value, and then we will get RMSE. And RMSE of our model, let's see, for the training set it is about 0.9, but for the test set it is about 1.27. Okay, so that means if our model predict the rating, which is for example 3, then the actual value of that rating may be belong to a range from 2 to 4, because the error over here is about 1.27.
We also using root mean square error for collaborative filtering evaluations, and compared to the content-based recommendation, the RMSE is 1.27, and the RMSE for collaborative filtering evaluation is kind of smaller, 1.017, and that this method is kind of better.
Now come to the evaluation of the G-local-K. As we said that we already did the experiment with the two datasets, the ML100K and ML1 million, so that we have some measurement after we doing the process. For the ML100K, we running in total 90 box, 30 for pre-training and 60 for fine-tuning. We can see that the average time of the pre-training is 4.2 seconds, and for the fine-tuning is 8.7 seconds. The root mean square error for train of pre-training is 0.83, and for the test is 0.93. However, in the fine-tuning it has decreased. For the root mean square error for training it has only just 0.71, and for the test root mean square error is reduced to 0.91. So that um, for the ML100K, the best record of root mean square error is 0.91. And for the ML1 million, we running 20 epoch, for the pre-training and 30 epoch for the fine-tuning. Uh, the average time of the pre-training is nearly 72 seconds, and for the fine-tuning, the average time is nearly 48 seconds. The train route mean square error of retraining is 0.71. For the test route mean square error is 0.82, and for the fine-tuning, the train route mean square error reduced to 0.69, and the test route mean square error still remain 0.82. So, uh, during 50 epoch of running, the best record of root mean square error of the ML 1 million is 0.82. So that we zoom to some conclusion that we can see it clearly that the running time, the running process time, it tend to scale with the scale of the data set in the size, and we can see that during the pre-training and the fine-tuning, the root mean square error is has reduced. It means that it has some improvement of the retraining and it support for the fine-tuning. And with the more data, the root mean square error they tend to decrease. And when comparing the three approach, the content-based, the collaborative filtering, and the G-local-K for both ML100K and ML1 million, we can see that the G-local-K has the smaller root mean square error when compared with the two traditional approach of the recommender system, and it has outperformed these two methods. So here are some reference of our project, and thank you for your listening.